Welcome back to another exciting episode of X-Ray Education. Okay, so this presentation is on just plain old electricity. And why is electricity important? Well, primarily because it turns out that if we're going to make X-rays, we're going to need some electricity. This is what we do. We take electricity and we convert it into another form of energy. And let's see how we do that. Well, we're going to talk about that later. For right now, we're just talking about straight up electricity. Now, remember from our previous discussion, protons are the smallest unit of positive charge. Electrons are the smallest unit of negative charge. Unlike protons, electrons are relatively free to move around. So, like if an electron wants to skip from one atom to another, then under some conditions, it can certainly do that. So electrons can move around. Good thing. Now, here's a quote. I don't know who said this, may have been me. Electricity concerns the distribution and movement of electrons and has little to do with the positively charged protons locked within the atomic nucleus. Now, can we use enough energy to get some protons moving? Why, yes, we can. But typically, we do not do that. It's much more efficient to move the electrons. Okay, electrostatics. Electrical charges, and you can think about like static electricity. There's a possibility when you're talking about electrification. You can have negative or positive electrification. So in other words, you can have a massive negative charge or a massive positive charge. But either way, you're still talking about the movement of electrons. So how would I wind up getting a massive positive charge? Well, I'm going to get rid of a bunch of electrons. I'm going to move electrons away from an area, and that's going to generate a positive charge. Negative charge, I can push electrons into an area. And I have some methodologies for doing that. Something I wanted to mention is this, because we were talking about lightning strikes the other day, and whether lightning strikes originate in the ground or in the clouds. You know, does lightning come down from the sky or does it come up from the earth? And the answer to that is yes. It depends. Okay, whenever there's a thunderstorm in progress, if there's a lot of electrons close to the ground, then the electricity potential there is going to be, you know, of course, electricity always flows from areas of strong negative charge to areas of less negative charge. So the electricity in that case, if the negative charge is close to the ground, then it's going to jump to the ground. If the negative charge is up high in the cloud structure, you know, you can think of this as being like these big thunder clouds. They're very tall, and so it's possible for there to be a large negative charge at the top of the clouds and a less negative charge, in other words, a net positive charge close to the ground. In that case, excess electrons from the Earth can jump up into the cloud, and so the lightning strike can actually originate from the ground to the cloud. That can totally happen. Remember, the Earth is an infinite reservoir of positive and negative charge. So it basically is whatever we need it to be. So we can use the Earth as a ground indefinitely. Now, here's some laws of electrostatics. Neutral charges, well, they don't do anything. They just kind of hang there. Negative charges repel one another. Positive charges repel one another. But positive and negative charges, they attract. This is going to come in real handy when we go to make X-rays. Inverse square law, don't forget, in addition to X-rays and in addition to light, the inverse square law also applies to electrostatics. So, the closer these charges get, the stronger the force is going to be. So if it's two positive charges and you start pushing these guys closer together, then the force of repulsion is going to get really, really high. They do not want to touch each other. Okay? Now, likewise, if a positive and a negative charge are in proximity, then the closer they get to each other, the more they're going to be attracted. So when these charges are really, really close together, then the force of attraction becomes irresistible. They're going to want to get together. And this is just a picture of the inverse square law as it applies to a light source. So up here is S, that's my source, and you guys kind of know the drill. This thing is a pyramid, right? Pyramid shape. And so if I look and, D2 is twice as far away from the source as D1, well, in that case, since I've increased my distance from D1 to D2 by a factor of 2, I've increased my area by a factor of 4, right? Because 2 times 2 is 4. And if we're talking about area, we're always talking about, a two-dimensional square. Okay, some laws of electrostatics. On any object that is electrified, the charges are going to try to distribute themselves as far away from each other as possible, basically. So if there's a bunch of negative charge on a piece of plastic or a piece of glass, then those charges are going to distribute over that as evenly as they can, because they're just trying to get away from one another. And concentration, you'll notice, like if you have a sphere, then the electrons are going to be evenly distributed. If you have this oval looking shape, the electrons are more or less evenly distributed. But if there is a point, is there a point to this discussion? If there is a point to this object, if there's like a sharp corner, then that's where you're going to find most of the electrons concentrated as they try to get as far from each other as possible. In this small area here, this area of lesser curvature, they're going to be more concentrated. And it always does that. There's nothing you can do about it. Now remember, negative charges are the only ones that move. And in reality, the negative charges don't move that much. As you charge, think of it kind of like a bucket brigade. As an electrical charge enters a conductor, then it's going to either push or pull on the electrons in that conductor, and if it's pushing on them with a negative charge, then each successive atom is going to push to the atom next to it, and so it's kind of like a chain reaction or a domino effect. And then at the other end of the cord, at the other end of the wire, we're going to have those final electrons are going to push on into our light bulb or into our electric motor, whatever it is we're trying to do with this electricity. And there has to be a circuit closed or else the electrons can't move, right? So insulators would stop our little chain reaction thing. Now, how can we electrify something? Well, friction, you guys are all familiar with that, I'm sure, especially during the winter, as like if you're at a department store and you're walking around and you reach over to grab a shirt or something off the rack and you touch that metal rack, zap, static electricity. Contact is another way of electrification, and then we can use induction, and it turns out induction is the most important from an X-ray standpoint. So here's some examples of friction. Like if you take a balloon and rub it on your head, then you can stick that thing to the wall or the ceiling because it now has a net positive or negative charge, and so the electrostatics will enable it to stick to another surface. If you comb your hair during the winter time, sometimes if you have like light or like thin straight hair, your hair might start to stand up on end. You electrify it using your comb. Contact. Okay, this permits electrons to move from one object to another directly. So here's the example of like we were talking about with friction. Okay, if I'm walking across a wool carpet or acrylic or something like that, and I'm building up a charge as I go, and then I get to a doorknob and I go to touch it, zap, it shocks me. Why? Because I just imparted my electrical charge to that object and I felt it flow through my finger. This is also known as a static discharge. And here's an example of where a static discharge can mess us up. Now, this never happens with CR and DR, but with regular film, this sometimes was an issue. If the darkroom was too dry, then it was possible to touch a piece of film and have a static discharge, and these are beautiful, aren't they? These tree branch static artifacts are, very distinctive. It's like, okay, I know exactly what that is. That is not the shadow of a tree that was overhanging the radiology department. That's a static electricity discharge. Okay, an electroscope, I don't really need to talk too much about this. We don't have one in our laboratory. I used to teach at another facility, and we did have these kind of objects. We had a Van de Graaff generator and a bunch of stuff. Anyways, if this metal knob here is at neutral charge. Okay, there's electrons floating around in it, but they're not really doing very much. If I take a glass rod and I rub it with wool or something, and I generate a static charge on it, and then I touch that rod to this ball, look what happens. I've got now all these extra negative charges here, all these electrons. Well, they're going to push their way down this conducting rod, and look what happens to these leaves down at the bottom. They spread out because they're being repelled from each other by that negative charge. This is just like an elementary school experiment. A lot of people, you've probably already seen that thing. Now, induction, this is important for us. So if you don't pay any attention to anything else, pay attention to this. Electronic devices such as electrical motors and transformers use induction. This is a process by which electric fields can act on one another without making physical contact. In other words, we're going to induce an electric charge without actually touching anything. This comes in handy over and over again. Now, electrodynamics. We're going to look at electric current, properties of conducting materials, circuits, and sources. Okay, and I promise this isn't going to go all day long. Now, here's the way current flow works. You can imagine, and I was talking about like a domino or a bucket brigade, but if you can imagine a conductor being kind of the same way. If I induce a current onto this conductor, it's kind of tantamount to me shoving a ball into this tube. Well, what happens at the other end? Well, this ball falls out, right? This is kind of how electrical currents flow through conductors. The individual atoms don't really move. They just pass the charge on from one atom to the next. And of course, the electrons always flow from high concentration to low concentration. So the electron flow is always negative to positive. It's never the other way around. Okay, so if we're talking about the quantity of electrons flowing through my circuit, that's measured in amps. That's just me standing there with a stopwatch and just counting the number of electrons that go by in a second, right? The higher the current is, the more electrons are flowing. And then the force with which these things travel. Okay, how fast are these electrons moving? Because they don't move at the speed of light, they don't move at a consistent speed. The higher the voltage is, which is this potential difference, the higher the voltage is between 2 points, the faster the electrons are going to move. And there's also opposition to current flow. Anytime, and it doesn't matter if you have like a really, really good copper conductor, it's still not going to like having current flowing through it. So what's going to wind up happening, those atoms in that conductor are going to get a little bit irritated, and they're going to start getting hot. So there's always going to be some resistance to the flow of current. Now we'd like to keep that under control. We don't want our conductor to get too hot, because here's something about conductors. Okay, the hotter the conductor gets, the less it wants to conduct current. In other words, as the heat goes up, so does the resistance in a conductor. Conversely, as the heat goes up, the resistance goes down in an insulator. So you can see that this is a recipe for disaster. If you have a copper wire with a plastic coating over it, and that wire starts getting hot, well, then it's going to get more and more resistant to the current. In other words, it's going to just keep getting hotter and hotter and hotter. Well, the jacket that's around it, the insulator, as it starts getting hot, and even if it doesn't melt, as it starts getting hotter, it's going to lose its resistance to electricity flow, and then you might have a short circuit occur even if your insulator is technically still intact. And that can wind up causing a house fire or something like that. You know, you don't want that going on. Oh, and direction of travel. In a DC current, the electrons always travel in the same direction, you know, round and around the circuit. In an AC circuit, it's slightly different. The way AC current works, and this has to do with the mechanics of the engine or the generator that created the current in the first place, alternating current is so named because first it flows away from the generator and then it is pulled back towards the generator. So you get this back and forth flow of electrons. Now, if your back and forth flow is through something like a light bulb filament, then it doesn't really make any difference. It's like whether the electrons are moving forward through the filament or moving backward through the filament, they're still causing high resistance and generating light. You know, that filament's going to get really, really hot, and it's going to generate light for us, right? And it's going to be nice and constant. If a device requires DC current in order to function, then that alternating current's not going to do anything for us. We're going to have to run that alternating current through some kind of a device that's going to change the alternating current to direct current. Then we can use it in a DC device. So AC and DC are different kinds of electricity. We can convert them back and forth though. So like say you're going to a tailgate party and you want to be watching a television. Okay, well, what can you do? How can you power a television from your car or truck 12-volt electricity, which is direct current, it's DC? Well, no problem. We just hook up a voltage inverter, and what that'll do is take our DC current and change it into AC, and then we can plug in our TV and we're good to go. Okay, now keep this in mind. The current is always measured in amperes, which is 1 coulomb per second. And a coulomb is a unit of, that's a quantity, a unit of quantity, and it is equal to 6.24 times 10 to the 18th electrons. This says charges. They're negative charges. Negative charge is always implying electrons. And this is basically just a flow rate, okay? Now that's a whale of a lot of electrons, isn't it? I'm not sure how Dude came up with that measurement. I haven't really, I studied it at some point in time, but like most things in X-ray, if it's not important, I don't keep it in my mind. So if you ask me a question and I don't know the answer, it's because nobody else cares about it. Potential difference. This is the force behind these electrons. The more force, the faster the flow. That's going to wind up being important for us. Now, voltage also sometimes is called electromotive force. Electro, electricity, motive, motion. Okay, this is the force behind the motion of these electrons. Now, usually this is measured in volts. In our world, we talk a lot about kilovolts, because how do we make an X-ray? Can we use 80 volts? Nope. We need 80,000 volts, 80 kVp. And don't forget about your resistance. This is the opposition to the flow of current, and it occurs everywhere. And so, you know, whenever we have resistance to an electrical current, we're going to have issues with heat. We have to get rid of that heat. Your generator cabinet's going to be generating heat. Your X-ray tube's going to be generating a lot of heat. We just don't want that to get out of control. Now, the resistance is always measured in ohms, and it depends on several things. The conductivity of the material. Materials that don't want to conduct electricity, or they will conduct, but grudgingly. Like a piece of steel, a piece of iron, something like that, that's going to get hot really fast. the length of the conductor. The longer the conductor, the higher the resistance and the more heat issues you're going to have. The diameter of the conductor. A really skinny conductor, I've seen little wires with current flowing through them actually burn in two because the resistance is so high. Skinny conductors have high resistance, thick conductors have low resistance. And then temperature, like we were talking about earlier. As the temperature goes up, so does the resistance in a conductor. What happens as the temperature goes up to the resistance in an insulator? Yeah, that's right, it goes down. Now, the material's conductivity depends on the material. The farther the valence band is from the nucleus, the easier that material is going to conduct electricity. So if we look at the periodic table, which is over there in the corner, you'll notice that there's a substance on there called gold. It's an element. Now, gold is a heavy element, relatively speaking, so its conduction band is far out from the nucleus, and those outer electrons are very loosely held, and so that gold conducts electricity like nobody's business. It is hands down, as far as I know, I think it's the best conductor we got, besides those superconductors that they use in MRI. But you'll notice that, like with really expensive computer components, they have gold-plated contacts. That's because it's one of the best conductors there is. Coming down from that, we have silver. Silver has the same setup as gold in terms of outer valence with loosely held electrons. Silver is a fantastic conductor of electricity. Coming down the chart a little bit further, we come along and we find copper. Copper has loosely held electrons in the outer band. Not as good as silver, not nearly as good as gold, but what is the advantage of copper? Okay, couple of them. A, it conducts electricity really, really well. It conducts heat really well, so we can vent heat off of a copper conductor. And the other thing is it's relatively cheap. We can go out and we can dig up in the ground and we can find copper, you know, a lot easier than we can gold. So we use copper for a lot of our wiring needs. Okay, more length equals more resistance, like we were saying, so the longer your conductor is, the more problems you're going to have. So if you're going to have, good idea to run an extension cord from a 110 volt outlet, you know, like way out onto the sidewalk somewhere? Not really. If you're going to use a really long extension cord, it needs to be a thick extension cord, because the longer that thing is, the more resistance you're going to have, the more heat's going to become an issue, so you can kind of compensate for length with larger diameter. Remember, the diameter is inversely related to resistance. You increase the diameter of your conductor, in other words, you have a bigger wire, then you're going to have decreased resistance. This is why a lot of times jumper cables are 4-gauge wire or even 2-gauge wire. They're very thick conductors, but they don't have all that much resistance, so they work a lot better. And temperature, as we were saying, this is directly related to resistance. And it's a vicious cycle. You know, once you get heat in a system, then it gets hotter, it gets more resistant. The increased resistance means increased heat. So you're just kind of chasing your tail. And next thing you know, you've got a house fire. This is why you shouldn't plug a crap ton of devices into one outlet. You know, the more resistance you've got, the more heat you're going to have, the more chances you have of sparking a fire. Remember Ohm's law. V is equal to IR, where V is equal to the volts, I is the current, and R is the resistance. So if we have V as being equal to IR, then if we're given any two of these quantities, we can figure out the third. And some people put it in like a little triangle here. So if we have the V and the I, then we can figure out the R. Just by using some, you know, so, okay, not only is V is equal to IR, but I is equal to V over R, and R is equal to V over I. You just have to divide both sides and make sure your equation balances. Power. Okay, so I know you know that a lot of systems, you know, it'll have like a power rating, and it'll say 30 kilovolts or whatever, or kilowatts, sorry. Power formula is this: P is equal to IV, where P is equal to the power, and the unit is watts. So in the equation we use a P, but the unit is watts, so that's abbreviated with a W. I is your current, measured in amperes, which is abbreviated with an A, and then V is your potential difference, measured in volts. So here's a question for you. Suppose I have a system that's capable of 1,000 milliamps at 80 kVp. Well then, what is the power rating for that system? Well, I'm going to take my 80,000, which is my volts, 80 kV, and I'm going to multiply that by my current, which is 1,000 milliamps, or 1 amp. So 1 times 80,000 is equal to 80,000, which means this system has 80 kilowatts of power. That's a pretty strong system. Okay, so series and parallel circuits. This is the difference. In a series circuit, all of your resistances are serial. So you have to run through each of these in turn, right? And so it's just like one big roundabout. With a parallel circuit, it's slightly different. Parallel circuit has all of our resistances in parallel. This means that every time I add another resistance, then I'm adding another pathway for the electricity to take, and so these individual resistances, you know, they're going to stay static, but the total resistance in the circuit is going to start going down. Now, if my voltage is held constant and my resistance goes down, what must be happening to my current? Yeah, exactly. It's going to go up to compensate. So next thing you know, I'm going to have a whole lot of current running through the system. So imagine you're at your house and you put a microwave and a couple of lamps and a toaster oven and one of those air fryers. You put those all on the same circuit and you turn them on simultaneously. What happens? Well, you're probably going to pop a circuit breaker, because your circuit breaker in your kitchen is supposed to be set for about 20 amps, 15 to 20 amps. So if I'm adding more resistances then, and my voltage stays the same, then my current is going to go up, and my current's going to go up to a dangerous level to where I could, you know, maybe burn my house down. But before that happens, the circuit breaker is going to trip and cut off that circuit. And it's not going to come back on until I remove some of those resistances. So this is a safety method, you know, circuit breakers, and we have those in our X-ray system too. You know, if you try to run your X-ray tube with too much energy, then you're liable to trip a circuit breaker. All right, super. So you guys made it through my electricity presentation. Congratulations. Now then, stay tuned to this channel, because I'm going to be back with some more information now that we've figured out a little bit about the atomic structure of our materials. We talked about that some, and now we've talked about our electricity. Now we're going to look at some of the equipment that we use in X-ray and how we use that equipment to actually make images. All right, so come back and visit X-Ray Education for more exciting information.